Welcome to the lecture series on GPU architectures and programming. In the last lecture, we gave a nice example of optimization using the shared memory with respect to matrix transpose computation, and we saw that how using shared memory you can have very nice global load and store access patterns, and that leads to order of magnitude reduction in the total execution time of the transpose, as we saw from our kernel analysis statistics. By the way, I will just like to repeat that these statistics have been revealed using our system, where we have a Tesla K40 GPU card. Now, of course, for if you are trying to have results of profiling using NVProf or some other your favorite profiler for this kind of computations, the timings you are going to get, of course, will depend on the system you will be using, right? Here, just use these values for comparison among the different optimizations we show, because we are running all the different examples or different variants of the same operation in the same system. So, consider the relative performance values here. So, one interesting thing that we started showing here was that since in our way of computation the shared memory load was not coalesced. So, if I just recall our original diagram of how the different locations in the input matrix, the output matrix, and the tile was getting accessed. So, let us say this is the tile and this is the output matrix. So, from one input block, one row, you are writing here row wise, and then you are loading the data from the tile column wise and writing in the flipped block location row wise, right. So, these loads from the shared memory are not coalesced, and that would create bank conflicts in the shared memory. So, what is a bank conflict? The shared memory is not a contiguous piece of memory element, rather it is arranged in a set of banks. So, in modern GPUs with as we know that with GPU families, what the NVIDIA defines what they call as compute capabilities, right. So, since we are working on a device with compute capability 3 and above, we have the shared memory with 32 banks. So, essentially what is the idea of a memory bank? Now, a memory is arranged into these different sets. Let me redraw this picture in a nice way. So, the memory, when I say that the memory segment is banked, it is not that I have a one big large chunk of physical memory. Rather than that, the physical memory is split into smaller chunks of physical memory, and they are all accessible in parallel by the hardware, right. So, let us say this is the read write bus, and you can access all these banks in parallel. What is the good thing about this? When you read or write data into the shared memory, let us say this is bank 0, this is bank 1, this is bank 2. Since you can access them in parallel, and if your arrangement of data, let us pick up some array A0, A1, A2 like that, these are consecutive locations, right. So, when you are reading or writing the data, consecutive values will be distributed across banks like this, right. So, when you are writing the data, consecutive locations get distributed. Now, the amount of data if you are writing, if it is same as the number of banks, then there is no conflict in terms of the writes. So, what do I mean by conflicts? To think in this fashion, that since I have a warp of size 32 and with devices of compute capability 3 and higher, I have got 32 memory banks. So, an entire warp of thread, if they are actually going to store data or load data to or from the shared memory in consecutive locations, all those locations are going to map to different memory banks, right. because I have 32 memory banks, 32 consecutive locations. Suppose I am loading data from these 32 locations using a warp of 32 threads. I will simply access all of the banks in parallel and I will load the data, right. So, that will be one load. But consider the situation that when I am doing the shared memory load in our case. So, I am loading the data from a column in the matrix and a column in the tile size is 32 cross 32. So, essentially the column will get what we call as a 32-way conflict, because the entire column is located in one bank, right. So, then the question comes that how much overall number of loads should happen. In this case, in this specific case, we see that it's almost a 16x time required, right. Now, this, as we have discussed with people in the NVIDIA forum, this is something that is architecture dependent. Although this is a 32-way conflict that we are getting, still the memory banks have got a read write speed with which they can actually read or write 64 bits per cycle. Now, since in this case our data is each of size 4 bytes, so although the conflict is 32 way, the number of loads are increasing here by a factor of 16, because the data size is half with respect to whatever I can load from the bank using its bandwidth. Since in this case for our machine it is 64 bits per cycle, that means 8 bytes in parallel. Now, what does that mean? To be more specific, suppose I am working with 8 byte data. If I am working with 8 byte data, let us say double precision floating point, and then when I am trying to load such a column of data, the data sizes are 8 byte with all the data positions located in the same bank. I have a 32-way conflict, and then since the data width is equal to the bank's memory bandwidth, that is the number of bits I can access per clock cycle. So, in each load operation I will just load one instance of the data. So, in that case I will have a 32x increase in the number of loads. In this case it is 16x, right. Some other interesting activities, as you can see that since we have got nice access patterns with respect to global loads and stores. So, both of them are the small, there is no increase based on the problem that we have been discussing. So, this is the good thing about the shared memory, and also we have pointed out the bad thing, that due to bank conflicts I have got a huge increase in the number of shared memory loads, right. Now, how do I decrease this? Because this again is leading to some loss of speed up. Whether the question is whether it is possible to somehow rewrite the code in such a nice way that this issue of shared memory bank conflict can be resolved. Again, I will just summarize this idea of bank conflict. It is similar to memory access coalescing. So, in a global memory I can access consecutive locations. Similarly, when I am if a warp can access consecutive 32 locations in parallel, and so if that is the amount of data that is required, it can be fetched from the global memory in one global memory transaction. Similar for writes. Coming to shared memory, it is arranged in banks, and consecutive locations, consecutive data points are written by the threads in a warp in consecutive banks. So, if I have 32 banks and suppose I am going to write 32 consecutive data points, it will be written consecutively across the banks, but unless it is such a regular access pattern. For example, suppose I am trying to write data in a column wise way, or write in a read or write in a column wise way. That means, suppose all the threads in the warp are trying to write for the tiles column, that mean, or read from the tiles column, that would mean in both read or write operation I am accessing the same bank, and that gives rise to a 32-way conflict. Now, this 32-way conflict is also something I will like to explore a bit. So, what do I really mean by this? So, for that let us take an example for some other cases of conflict. So, consider some other threads. So, let us say thread ID 0, thread ID 1, thread ID 2, thread ID 3 like that, and let us say this is my set of memory banks B0, B1, B2, B3. Now, if the access pattern is like this regular, then there is no bank conflict, right. This we have already discussed. Now, consider some other access pattern. For example, let us say the threads access in strides of 2, right. So, T1 and T2's access are separated by 1 hop, then T0 and T1's access are separated by 1 hop, right, and then let us say T2 and I continue this pattern that T1 and T2's access is again separated by 1 hop, right, and then T2 and T3's access is separated by 1 hop, right. So, let us consider this pattern, right. Now, let us understand what is the number of bank conflicts I get. Since I have got 4 threads accessing 2 banks, right, and for each bank I am looking for 2 transactions. So, this is like a two-way conflict, right. Now, consider this pathological scenario that every bank is considering to access data all from bank 0, like happened in our example that we are accessing a tiles column. So, that would mean and the tile width is equal to the number of banks. So, if I do a modulo mapping, then all the data in the column will fall into the same bank, and that would give rise to this scenario. So, considering 4 number of banks, here I have a 4-way conflict. Similarly, in this problem we had a 32-way conflict. So, this is how the idea of shared memory bank conflict builds on. Now, just to get some idea that okay, suppose I am just I find out some way to resolve the bank conflict, and I want to compare that with a normal shared memory copy operation. Before we get into the way we do a shared memory bank conflict resolution, let us look at some performance figures with respect to a simple copy operation. So, you have an input matrix, you access that input matrix using the idea of tiles, and then so as you can see is the similar code that we had again. So, we are continuing with our definition of tiles and blocks. I can have blocks containing which are addressing multiple tiles, or one block of one thread block contains the same number of threads as in the tile. Both are fine. In one case the loops will be active, in the other case the loops will only iterate once. But what is going on here? So, this is a simple copy kernel. That means the data is copied tile wise, right. Input data gets into a tile, and then that tile full of data goes into the corresponding output matrix, right. So, this is the simple accesses we are doing here. Now, we want to compare this simple copy kernel with the situation of an optimization where we are doing a bank conflict resolution. So, first of all, we make an observation that if I am just doing memory copy from one input matrix to an output matrix, what is the time taken if I am using shared memory? So, as you can see, it is some 3.8 millisecond, which is much smaller if I compare it with my results on shared memory based transpose, which was 6.142, right. In both cases we are using shared memory, but I can attribute this difference due to those bank conflicts. Why? Because in both cases my global memory loads and global memory stores are all coalesced. Here also, as you can see, that the global memory loads and stores are all coalesced along with shared memory loads and stores, right. So, my problem with the code where I have used the shared memory, but I computed the transpose was that the shared memory had bank conflicts while doing the loads for writing into the output array. So, how do I resolve this bank conflict is the primary problem we want to solve here. So, the idea is very simple. Keep the code exactly same as it was, increase the tiles dimension by 1 in one direction. But the question is, how does this really help? Okay. So, let us try to figure out that what is the effect now if I increase the tiles dimension by 1. So, this is our access pattern that we have already discussed, but now we are trying to figure out that for this tile, if I now draw a magnified picture of this tile, so this dimension in the x direction has been increased by 1, right. So, let us try and figure out, first of all I would just like to repeat that we have just increased the dimension, nothing else has changed in the code, nothing else has changed in the code, which means I do not really use this extra location for copying data by any of the threads, or I do not really load anything from this location and write back somewhere. So, this is the last column which I do not really access, I do not write here, I do not read here, right, but I use the rest of the 32 cross 32 locations for whatever earlier operations I was doing, basically all the same operations, right. So, when I have written the data here, let us understand for one block I have done a row wise access and written the data row wise, right. That would mean the threads and the corresponding locations, if I just write the IDs of the locations, they are getting mapped nicely like this. I do not write anything here. And that is how it continues, right. This is what is going on, right. Point is, now what happens to the arrangement of the data in the banks. Now, in the x dimension of the tile, I am mapping all these locations to 32 banks, and I have got 33 locations to map per row, right. So, in terms of the banks, how really is this mapping happening? So, this data would go to the data for the location 0 goes to bank 0 like this up to bank 31, and then this location gets mapped to 0, right. Now, that is what has changed. So, now if I try to map this layout in terms of the shared memory's actual layout. So, let us rewrite the bank locations B0, B1. I am just writing the shared memory banks now, right. So, I have up to B31, right. So, I load the 0th data, first data, second data, then up to 31st data, and then I have a do not care value in B0, then the 32nd data in B1, 33rd data in B2 like this up to 63rd location, right. And then no, sorry. So, since the 32nd location is in B1, so what do we have here? It has to be the 62nd location. Please understand this, this is very crucial. Since I have put in a don't care here, so now your B0 starts getting mapped from B1 location, right. So, sorry, here it should be shifted to 62. But then where does 63 goes? 63 would now get mapped in B0, and then after that there was a don't care, right. I am removing this. It was initially drawn just to understand the banks, but since I have a physical picture, just to avoid the confusion, we remove this. This is the enlarged view of the tile, and this is the corresponding mapping in terms of the actual shared memory banks. So, 63rd data point is in bank 0. After that, we have this don't care. So, then 64th data point is then in bank 2. Now, if I continue like this, so this is in B2. So, what should we have here? Here we should now have the 93rd data point, right. So, that would bring the 94th and 95th data point in banks B0 and B1, and here you get a don't care. Now, consider what happens to the load instructions. So, I am doing a load by column, right. So, now when I am trying to access the data, look at the loads that will happen, right. So, in the first load, I get all the data, right. So, essentially first of all let us point out some data points that I want to load. Assume that I want to load from this column, right, because just to keep consistency, let us go back to the original code and see what were we really loading. This is the code without bank conflict, and it's just that I am loading from a column, right. So, as a representative column, let us just take the first column, which was in our original implementation, where I did not increase the width of the tile. All this data was going to bank 0, right, 0, 32, 64, 96, all were going to bank 0. But now what is the location? As you can see, 0, 34, 64, like this, it is all now distributed, right, across the banks. So, you have 0, 32, 64, and like this up to the end, everything is distributed across the bank. They all get out with a load 1, right. Similarly, in the next, what do I get? In the next column, what do I have? 1, 33, 65, 97. If you look 1, 33, here you will have 65, and similarly like that. So, this is the output that you get in load 1, and in the next access you are going to get all the data in the second load, and so on and so forth. So, now due to this insertion of an extra dimensional extra column in the tile, I have got memory padding in the shared memory, and this memory padding is actually removing the conflict that was happening in each load instruction of the column in the tile. When I look at that access in terms of banks, I am always accessing all the banks parallelly. So, I do not have any conflict while loading the values for the column from the bank shared memory. So, this works like magic, but it is only that simple. All you do is you modify the tile's definition by doing a padding of an extra column. It changes the entire arrangement in the bank. So, every column of data actually is now diagonally distributed in the bank, and due to that distribution, you have that column uniformly distributed across different banks, and they can all be accessed using a single load instruction. So, that is the wonderful optimization I would say. Now, with that we have a very reduced execution time. As you can see, it is almost 4.1 millisecond, and all the shared loads, shared stores, global loads, global stores, all are coalesced, right. And as you can see, this is almost similar in execution time. It is only 3.85 with the normal copy operation using shared memory, right. So, here you have successfully resolved all the bank conflicts, and your code executes with very minimal execution time, and it is almost comparable with a normal simple copy operation without doing the transpose, right. This is how, if we understand the memory hierarchy correctly, we can remove bank conflicts and do a better optimization with respect to data. With this we will like to end, but before that we will like to revisit some other example. If you remember the way we spoke of transpose, we did a 2-level optimization in the transpose, right. The first computation we did was just to change the x and y indexes in such a way that you do not completely flip the x and y for y and x, but you recompute the x and y for the original transpose kernel using shared memory, such that they represent the flipped block location. And then in the flipped block location, you flip while reading from the tile, and the reason for doing that was you achieved very nice patterns with respect to read and write, but you did a overall matrix transpose. Now, it may be required that you do not need the entire matrix to be transposed, but you only need to do a tile level transpose. What essentially I mean is, so suppose you have this entire matrix, you do not want to change the relative positions of the blocks, you just need to do local transposes here, here, here inside the tiles. You want to flip inside the tiles, right. So, that would mean all you do is you do not do any recomputation of the block IDs, but rather you access the data, I mean from the input load to a tile, and then you read from the tile column wise and write to the output data without doing the intermediate flipping of blocks. I will just repeat. If you remember our optimization, which is here. So, it is a 2-level thing, right. First I flip the blocks and then I flip the location of read from the tile. Consider this is not done. So, you do not flip the block. So, you are reading and writing from the same block, but while reading from the shared memory tile, you have flipped. That means you read column wise. So, that would effectively do a fine grained transpose, as we call it here. So, what essentially I mean is I do a local transpose. That means I do not change the block's position, but inside the same block I am now reading in a different way and writing it back. So, I am effectively just inside the same block I am doing the transpose operation. So, you compute the index to read, fair standard, and then you read the data in your definition. So, here we are defining block as the thread, I mean thread at the tile using the name block here, and then from this you write using the flipped pattern that we discussed earlier. Suppose you do not want to do this, but you want to do a block level transpose. That means you just flip the location of the block, but you do not change the internal arrangement of data. Again, if I go back here, so if I do not do these operations, then I do not flip the position of the black, but suppose I do these operations, but then I do not do this flipping here, I do a normal read write. What would that mean? I flip the location of the block by this, but then I do a normal read write. So, that means inside the block the relative offsets of the locations do not change. So, that is what we can call as a coarse grained transpose. So, for fine grained transpose we have an execution time as given here, and then for the coarse grained transpose as we discussed. So, as you can see, I computed the index in first, that is how to read, right, and then I flip the block locations using the original segment of code I showed, and I use this flip block location to compute the index out where to write, and then I do a normal read write. I read from iData using index in to the block or the tile, and then from the tile I use a normal access. As you can see, there is no flipping while reading and writing from the tile. You straight write to the tile, you straight read from the tile. You use index in to read from indexed iData, you use index out to write to OData. Now the difference is this index in is the original usual consecutive location index, but when I use the index out, I have flipped the blocks using the first part of the switching, but I am not using the second part of the switching. Here I don't read by column, I read by array, I read by row from the tile. So this is the coarse grain transpose. That means this block comes here and some relative location of data remains same with respect to the block, right. So these are also associated operations that you can look into, and we also provide the execution time and other things of that. With this, we'd like to, you can actually look into these data points, try and compare. With this, we like to end this lecture. Thank you.